And we'll say hold on and hold off while we plot these other things. Let's plot our transmittance. We'll make that a blue line. And then I also like to plot the conservation. So we can do it really easy, just R plus T, and we'll make it a dotted black line. Let's set our axis limit so it's not constantly rescaling on us. That can be irritating. We want to start at the first frequency. We want to end at the last frequency. Y limit. What we'll notice, our transmittance and reflectance should stay between 0 and 1. However, because we're showing reflectance and transmittance before the Fourier transforms really are done, we'll see this dancing around. So in order to see it dancing around, we'll display slightly outside of the 0 to 1 range. So we'll go from minus 0.1 up to 1.5. We'll label the x-axis as frequency. And we're actually displaying it in hertz, which could be ugly, and we can fix that. And we'll give this a title too. Reflectance and transmittance. And we should have our draw now as well. Okay, we typed a lot of code, so let's see what happens, and hopefully we haven't made any mistakes. Hey, look at that. So our pulse is entering from the left. I know the amplitude scale is jumping around. Notice how slow this is going. Two reasons for this. One is because we're updating the graphics every single iteration, but the other one is that we're doing these Fourier transforms. These are very time-consuming, expensive calculations. We'll notice that the transmittance curve jumps up as soon as that pulse leaves the grid. And then we see our little pulse that gets reflected because our perfectly absorbing boundary wasn't perfect because of the numerical dispersion. But this is essentially it. That's really just noise. It's a 0 pulse. And our transmittance is flatlined at 1, and reflectance is flatlined at 0. That's what we wanted to see because we're simulating transmission through air. There's no reflection from air. Now, what if we wanted to speed this up? Well, we have our trick here. We can update this every 10 iterations. Let's run it and see what happens. Much faster, much nicer, a little bit more choppy, but that's okay. The last thing I want to add is a nice, pretty plot of transmittance and reflectance. So let's go ahead and do that. We'll tell this to update every 100 iterations. So it won't make a whole lot of sense while we're watching it because it'll be so choppy, but it'll get to the answer much more quickly. So we're going to add a whole new section now to generate our pretty plot. Generate a professional looking plot. I usually don't spend a lot of time dressing up graphics that appears inside of a loop because that all takes time. Like for example, just adding a legend for whatever reason is really time consuming in MATLAB. So I'll usually keep my graphics rather primitive inside loops, but once something's done calculating, then I'll generate a nice professional looking plot. So here's a good example of how this is done. So we'll initialize the figure just by CLF. We get rid of whatever's there. All right, now we'll plot our lines, plot our data. We're going to use the plot command, and we're going to get a handle to it because I'm going to go back and change some parameters. So this H is a handle to what we've just plotted. Along the x-axis, we'll put frequency, but I don't like numbers that are 10 to the 8th, 10 to the 9th, that kind of thing. So what we'll do is we'll divide by gigahertz, and that will then put the x-axis in gigahertz quantity, 0, 1, 2, 3, 4, 5, and it'll look much nicer. Reflectance we'll put on a percent scale, so we multiply by 100. We'll make it a solid red line, and we'll give it a line width of, let's say, 2. Now we want to plot our other line, so we need to do the hold on, hold off thing. And inside here, tell you what, we will just copy and paste this plot command. We don't need the H, we just need the handle to that first one. Plot transmittance. We'll make that a solid blue line. And we'll plot our conservation. That again, we'll make a dashed black line. This is a convention I always use: red for reflection, blue for transmission, and black for the conservation. And I will always plot my conservation because it should always be 100%. If it's not, it tells us something's going wrong. Now, it won't be 100% if you incorporate gain or loss into your simulation. However, even when I want to incorporate loss, I will not turn on the loss at first. I'll run my simulation, make sure conservation's obeyed, and then I can turn it on and I have that extra degree of certainty that things are right. It's never a 100% guarantee. Okay, so at this point, I should have plotted my lines. I want to do some more dressing up. So let's set the view. Let's set the x-axis limits. We start at frequency 1. We go all the way up to the last frequency. However, remember we divided by gigahertz to put everything in units of gigahertz. The Y limit now, let's just go from 0 to 105. That gives us a little bit extra white space at the top to look at that. Now we're going to use this handle to dress up the figure window a little bit. I want to get a handle to the parent. So the handle H just points to everything associated with the line that we've just plotted. I want to modify things about the graphic axes themselves. So that's the parent. So H2 will be a handle to the parent. And now I can go ahead and set properties. So we can set the font size for the entire graph to something larger than what would be default. Let's choose 14 and see what happens. The line running around the figure window, we can make that a little bit thicker to look better. Maybe we want to give it a legend. So again, let's get a handle to our legend. We have 3 lines, and somebody who didn't watch this may not know what red, blue, and dashed black represent. So the first thing we plotted was reflectance, so that's the first thing we'll put in the legend command. Second thing was transmittance. And then the third and last thing was conservation. Now we want to set some properties about it. Let's set its location to north, outside. That will put the legend on top of the plot on the outside rather than right on top of data inside. All right, and now let's label the plot. The x-axis is frequency, now in gigahertz. And then the y label, the y-axis is percent because we're plotting reflectance and transmittance. If we didn't do anything about it, that percent sign would come out rotated 90 degrees because it's expecting to put a longer string along the vertical axis. So we'll specifically say to give it 0 rotation. And by default, it's center alignment, but it'll end up a little bit tighter against the axis than we want it. So we'll give it a different horizontal alignment, and we'll say to right justify it. Okay, we typed a lot of code. Maybe there's a mistake hiding there. Let's run it and see what happens. Remember, we're updating every 100 iterations now. So it'll look a whole lot more choppy, but it will run faster. And it's running this slow because we're doing 1,000 Fourier transforms every iteration. And those really are integrations. Okay, and there's our final plot. Let's make this a little bit bigger so we can see what's going on here. There's nothing interesting, but it does look nice. We see that our transmission curve and conservation curve are essentially overlapped and flatlined at 100%, and our reflection line is down here. We've labeled our x-axis as frequency in gigahertz and the vertical axis as percentage. If I wanted to dress this up further, I would look at the number of digits here, and I'd see 2 digits, 1 digit. And I would probably make this a 1.0, a 2.0, 3.0, 4.0, 5.0. That's beyond the scope of this computer session, but those are the types of things I would look at. So I think this is a pretty attractive plot. And at this point, we have a fully functional, rather feature-rich, one-dimensional finite difference time domain code. The only thing we have left to do is build in a real device, which is in the next computer session. So thank you.